And we are live.
All right. Hi, everyone. I'm Dr. Hunter Bennett. I will be the moderator for this session. I'm also joined by Heather Hamilton and Eva Maddox. All of us are from Old Dominion University. We'd like to welcome you to our wearables session. We have a lot of great presentations. So we have 12 total presentations. We have them kind of broken up into 3 blocks. So we'll do 4 presentations. Back to back, and then we'll have about 10 minutes of questions pending time. If you will, in the audience, will you write your questions in the chat box? Please add either the person's name, presenter name, or their number that's associated with the presenter to help us identify and kind of quickly go through those questions. And then we'll work with the presenters afterwards. All right, and I want to remind you that after our session is over, the presenters will be in the spatial chat S4 Muybridge and available to answer further questions that we don't catch here. So our first chunk is going to be over kind of topics surrounding Gait, and we'll get started with our first presenter, Tian Tan. Should have.
Okay, can you see my screen?
Yes.
Okay, great. Thank you for the introduction. Today, I will be introducing an inertial sensor and camera fusion model and how we used it for estimating knee adduction moment and flexion moment. I would like to acknowledge all of my co-authors. Knee osteoarthritis affects millions of people. Measurement of knee adduction moment, KM, and flexion moment, KFM, can be used to evaluate the risk of osteoarthritis progression. It can also be used for gaiter training to reduce knee load and knee pain. Currently, the measurement of knee moments is performed inside Gait laboratories using grounded devices called force plates and optical motion capture. These devices are accurate, but they are very expensive and would confine the measurement environment. In contrast, the inertial sensor IMU is cheap, small, and light. It has recently been proposed as an alternative sensing approach for knee moment estimation, but the accuracy is generally lower. Apart from IMU, cell phone camera is another easy-to-access sensing approach that osteoarthritis patients can use in clinics or at home. Some computer vision studies have already demonstrated that fusion of IMUs and cameras can enable more accurate estimation of kinematics. We hypothesized that they can also be used for more accurate estimation of knee moments. In our experimental testing, 2 cell phone cameras were placed at the right side and the back of the treadmill. Meanwhile, 8 IMUs were placed on the pelvis, trunk, both sides, shanks, and feet. Apart from these 2 sensors, we also used an optical motion capture system and an instrumented treadmill for ground truth measurements. The blue arrows represent ground reaction forces, and the dotted lines represent moment arms from the center of pressure to knee joint center. The ground truth 3D moments were computed as the cross product of moment arm and ground reaction force. The KM and KFM are the second and the first component of 3D moments. In our experimental testing, apart from working normally, subjects performed gait modifications. Previous studies showed that modification of foot progression angle, step width, and trunk sway angle could potentially reduce the knee moments. So our target users might want to modify these parameters. A monitor was placed in front of the treadmill to provide real-time feedback. This slide shows the model we used to estimate KM and KFM. We used OpenPose to extract 2D positions of shoulders, knee, and ankle joints, which were used as the model inputs from the camera side. The angular velocity and acceleration were inputs from the IMU side. Those inputs were fed into 6 identical recurrent neural networks to predict the ground reaction force and moment arm components. Those components were combined through the cross product function to be the KM and KFM. This model was trained and tested by the data of different subjects using a 5-fold cross-validation approach. Subjects were randomly divided into 5 groups. Then the model was training and testing were repeated 5 times, with each group used as the test set once and the other 4 groups combined as the training set. The root mean square error of the proposed model was 0.5% body weight times body height for KM estimation and 0.7% weight times height for KFM estimation. It outperformed prior IMU-based models proposed in the past 2 years, possibly because of different sensors and different model architectures. To investigate whether sensor fusion could improve the estimation accuracy, We also built an IMU-only model by only fitting the IMU features and a camera-only model by only fitting the camera features. The right figure shows that the Fusion model obtained a significantly lower root mean square error than IMU-only model or camera-only model for either KM or KFM estimation. This figure shows that the proposed model detected peak moment differences between gait patterns. During experimental testing, subjects performed modification of foot progression angle by working with towing gait, normal gait, and towed gait. It's obvious that the towing gait significantly reduced the first peak KM. Meanwhile, a towed gait significantly increased the KM. There were significant differences between each pair of orange bar and also each pair of blue bars. Meanwhile, there was no significant difference between adjacent orange and blue bars for any gait pattern, indicating that the model is applicable for modified gaits. In summary, we used 2 cell phone cameras and 8 IMU sensors to estimate the knee adduction moment and flexion moment. We demonstrated that the Fusion model significantly outperformed IMU-only model or camera-only model. We also demonstrated that the proposed model is applicable for a range of working gaits, thus potentially facilitating gait retraining. Thank you for listening.
All right, thank you very much. Next, we have Michael Potter. Great.
Good.
All good.
All right. Well, thank you for the introduction. I'd like to start by thanking my co-authors for their work on this project. And also I appreciate the introduction with Tian and talking about, there's all these benefits for using IMUs for estimating kinematics out of the lab, but there's still a lot of improvement that needs to be made. And rather than try to have you digest this title here, I want to start really by motivating this a little farther. Oh, why is it not working? So we know that we have really good ways to estimate kinematics within a lab, but if we really want to get outside the lab, we need new methods to be able to do this and ask a lot of new interesting questions. As Tian mentioned, IMUs are a really attractive option for a lot of different reasons. And in one approach, we can put these IMUs on every major segment of the body. And as Dr. Fleissig talked about in his Borelli Award speech, we can integrate these raw signals and actually get estimates of the kinematics. And the real challenge that comes into this is that when we integrate noisy signals, we're going to get integration errors, commonly known as IMU drift. And so we need ways to correct for this drift. But we can actually exploit a lot of things about this system. For example, we know that the foot is going to be approximately 0 velocity during stance phases. We know that these limbs aren't going to be coming flying apart and we'll have a common joint center. When the IMU is still, we know that the accelerometer embedded within it is giving us an estimate of the direction of gravity. And sometimes we know that a joint may be acting like a hinge or something else. But one of the areas that still remains particularly challenging is in degrees of freedom that have really low signal to noise ratio. So I'm going to zero in on one of those for the purpose of this talk and talk about improving estimation of the hip internal-external rotation angle, where that's a real challenge. And propose a measurement that I'm going to label the soft hinge measurement to actually help us improve these estimates. Now, we're going to start with something that's probably a lot more comfortable for a lot of you, which is that the knee acts kind of like a hinge. And this has been exploited a lot of times. And so here I have kind of this graphic of the pelvis, thigh, and shank. And the idea is the shank and the thigh each have an axis predominantly aligned with knee flexion, and that those should be pretty much aligned most of the time. And if we give a probabilistic treatment and correction, we're going to give it some wiggle room and some uncertainty within that. And the idea that we had was, while the hip doesn't act like a hinge, we actually do have realistic ranges of motion. We don't expect the hip to be turned around 180 degrees for long periods of time. And so what if we try to exploit the same kind of probabilistic hinge correction by aligning the flexion extension axes, but giving really high uncertainty to it so that we can still capture the other ranges of motion within this. And then we're going to embed this within a method that I developed for full lower limb kinematic estimation that already takes advantage of all of those constraints that I talked about on the previous slide. And now we'll see if adding this soft hinge constraint for the hip can actually improve our estimates of hip internal rotation. So to evaluate this, we had, from a larger study, 5 subjects with reflective markers and IMUs. They each walked with 6 different types of gait. So this was 3 different speeds of forward walking, a backward walk, and then a lateral right and a lateral left shuffle. And then we're going to estimate the kinematics. And so here you see a single stride for a single subject of the left hip internal external rotation angle as estimated by marker-based motion capture, and we get some profile. When we estimate with an IMU-based method, the one that I developed without the soft hinge constraint, we'll get a different estimate, and we're going to have some difference between those 2 estimates. And then the hope is that by adding the soft hinge constraint, we actually reduce this difference. And we're going to evaluate this by this metric of improvement, which is basically a measure of, are we getting closer to estimating these IMU-based metrics? Are they getting closer to the MOCAP estimates? And so are we improving? And so the results, so this is mean improvement across all subjects. And in the rows, we have the 3 degrees of freedom of the hip. And in the columns, we have the 6 different types of gait. And I want to draw your attention to a couple things that are really amazing. So one's the flexion extension and abduction angle. We don't really see big improvements, but that's okay, because that's not really what this introduction of the soft hinge was meant to give us. But we're not degrading them. So there's nothing about implementing this that's actually hurting our estimates of these other degrees of freedom. But we do actually see that the internal rotation is improved by this, and maybe even over long time periods, we may even see further improvement with this. And importantly, this isn't just true for forward and backward walking, where you might expect the hip to be predominantly acting in flexion, but it's also true for these lateral walks that have very little flexion, but very high abduction motion within them. And so we see from this that the soft hinge correction is really promising in improving our estimates of internal rotation without affecting the other degrees of freedom. And importantly, that this is holding over a wide variety of gaits, and really promising for application for arbitrary gait. So looking forward to questions and a meeting with people in spatial chat later. I'd like to thank my sponsors and ASB and have some references. Thank you.
Thank you, Michael Potter. Next, we have up Patrick Slade.
Can everybody see that okay?
Yes.
Great. So today I'll be talking about a system that I developed with collaborators at Nimble, and basically it's a IMU motion capture system that's wearable and open source. And so we've built this for the biomechanics community, and we think you might be interested in using it for your research or classes or whatever it might be helpful for. So clinics are really amazing. They allow us to do a lot of things. They can allow us to diagnose musculoskeletal disorders, provide interventions, or monitor movement. But unfortunately, they can only reach patients who live near a clinic, can afford a clinic, or have time to come in. And so the goal of this project is to extend the reach of the clinical tools by providing a wearable and real-time motion capture system, so we can translate these clinical tools into at-home solutions. So our system is the OpenSense real-time system. And you can see here it consists of a microcontroller, which is basically a Raspberry Pi and some other little boards. It's worn on the hip. You have a little rechargeable battery, and then you have a system of IMUs that you wear on different body segments. Some details about the system are that it computes kinematics in real time. So this is all done on the Raspberry Pi, so it's all local hardware, which is nice. It uses wearable sensing and computation. So again, you're using just the IMU system and then the Raspberry Pi to compute the kinematics. It is fully open source, so it's built on OpenSim. So you can easily extend it to other biomechanics analyses, or if you want to customize it or add, feedback or something, it's quite easy to do that. And then some more fun details about why it's maybe more friendly than commercial software or commercial systems is it's low cost. So it costs about $100 for the base unit and $20 for each additional body segment that you want to track. The total weight is 400 grams. You can record for about 4 hours on one battery, and you can just swap them out if you want to keep going. And you don't need to solder or code to assemble it. So we've really streamlined everything and literally made it plug and play with the sensors. And it's customizable. So all you have to do is edit a single text file saying which body parts you put an IMU on, and the system will calibrate that and give you the kinematics for the joints that you care about. So let's see it in action. So on the left here, you see somebody moving. And then on the right, you see the reconstruction and OpenSim, which was done in real time on that portable microcontroller worn on the back. And so you can see here kind of the benefits of mobile computation. You know, it's very wearable. You can take it out into different environments. To start recording, you see that the participant is always in a quiet standing pose. And so we use that to initialize the system. The person just has to hold this pose for about 2 seconds, and then they can begin moving. And this pose can be changed for whatever custom application you'd like. And we performed studies, you can see here, comparing to motion capture to evaluate the accuracy of our system. And I'll talk a bit more in detail about that. So we performed one validation for walking where we had 5 participants walk for 3 minutes. And we computed kinematics with our system in real time at 30 Hertz. We found an average error of 4.4 degrees across 5 joints of the lower limb. Here you can see some sagittal plane joint kinematics that visually appear similar, and they have a high Pearson correlation coefficient. If you want to learn more about this, we have a preprint. And we also have detailed instructions on how to build the system. So I encourage you to check that out or come talk to me. We characterized that the system has about a drift of 1 degree per minute. So the error increases by 1 degree per minute. We also did an upper extremity validation where we had a cutting task and a lumbar range of motion task. Again, we found an error of about 5.6 degrees. And we mapped out how the computation depends on the number of sensors. So if you have more joints you want to track, it requires more computation, and the rate at which you can do so is a little slower. So we've provided this baseline here for you to pick your application project. Thanks. Looking forward to talking later.
All right, thank you very much, Patrick Slade. And for the last presentation of this section, we have Samantha Snyder.
Okay. Is my screen, oops, 1 second, sorry. Okay, is my screen showing?
Yes, it is.
Okay, thank you for the introduction. My name's Sam Snyder, and these are my co-authors, and I'd like to thank my co-authors as well, including my advisors, Dr. Miller and Dr. Shim. And our research is on prediction of knee adduction moments using instrumented insole and neural networks. So predicting knee adduction moments is important because of its relationship to knee osteoarthritis. Knee osteoarthritis is an extremely widespread disease that's often difficult to detect early on before pain is present. It's characterized by a loss of cartilage in the medial aspect of the knee, and this relates to knee adduction moments. Because all other things held equal, knee adduction moments put a greater load on that same medial aspect of the knee. And knee adduction moments can be used as a biomechanical risk factor for knee osteoarthritis. However, it's difficult to measure knee adduction moments outside of a lab because they require expensive lab equipment and knowledge of specific joint locations. So our goal of our research is to predict knee adduction moments outside, to be able to predict knee adduction moments outside of a lab setting. And we're doing that by combining custom instrumented insoles and artificial neural networks. The custom instrumented insole you can see up on the right here. It has 5 3-axis piezoresistive force sensors, and those are located under high pressure areas of the foot. And we had 9 subjects walk across force plates with motion capture wearing this insole, and that resulted in 100 cycles. We then applied a feed-forward recurrent and convolutional neural network to this data. It's been shown that artificial neural networks can predict knee adduction or predict joint torque with more accuracy than other types of machine learning models in the past. Specifically, feed-forward neural networks have been applied using different sensor inputs to predict knee adduction moments. So that was our first choice of a neural network to apply. And then recurrent and convolutional neural networks have been shown to be good time series predictors. So those 2 were applied as well. And overall, the goal was to determine how accurately this combination of an insole sensor, custom insole sensor, and neural networks can predict knee adduction moment, and specifically which neural network will predict knee adduction moment with the highest accuracy. So this is an example of data from one subject. These are the insole force sensors, which there's 15 force signals, and those are fed into each individual artificial neural network. And then from there, the knee adduction moment is predicted and compared in purple in these graphs here then for the entire gait cycle, and compared to the ground truth inverse dynamics calculated knee adduction moment. And as you can see in the plot on the bottom left, I extracted first peak knee adduction moment and second peak knee adduction moment, along with averaging the knee adduction moment across all 100 gait cycles, because these knee adduction moment variables relate specifically with knee osteoarthritis. And then these are the results for all 3 models. The bolded line is the average knee adduction moment, and the shaded area is 1 standard deviation away from that average. And visually, it's clear that the feed-forward neural network had the lowest accuracy, and the convolutional neural network has the highest accuracy. And overall, they all predicted with strong correlation coefficients between 7.72 to 0.96, with the convolutional neural network having the highest correlation coefficients of 0.89 to 0.96. So in the future, we plan to use this custom insole and machine learning techniques to predict knee adduction moments during daily living activities. This sensor and artificial neural network combination can then be used throughout the day to predict real-time knee adduction moment to better understand daily knee loading and knee osteoarthritis. Thank you.
All right, great job, everyone. Thank you very much for your presentations. We're going to open up the floor to questions. So we have several that have already been posed in the chat. We'll go over some of those together. We'll have about 5 minutes for questions before we start up with the next section.
All right, first question for the first presenter, Tian. From David, what are the next steps for your prediction algorithms? Do you plan on combining it with a haptic feedback tool such as Sage Motion?
That's a great question. So what we have done is the first stage, because all the subjects we recruited were healthy and young. We also care about the downstream clinical effects, like whether the model could generalize to patients. The study David proposed is exactly what we are hoping to do, using the Sage Motion to train real-time CAM estimation with variable haptic feedback, like even outside of the laboratory.
Great. Okay, next question will be for Michael Potter. From Andy, do you think this approach would work for internal, external rotation at the shoulder, slightly different anatomy and external constraints?
Yeah, I think it's an interesting question. My co-author, Stephen Kane, has a little more experience with looking at the shoulder than I do. I think there's a lot of challenge for kind of the position velocity things there, but the orientation estimates of the shoulder, I think, would would have a lot of potential. It might require modification of which axis you choose to align and kind of the uncertainty that you put around that. But yeah, I think it would have some potential there depending on how you implement it.
Awesome. Okay, next question for Patrick. Asal, is moving not difficult for the participants as they wear these sensors? With a follow-up from Ryan, along with Asal's question, how do you manage the long wires and prevent any wire strain or snagging?
Yeah, that's a great question. So that's the trade-off of using a wired system. It's easy to power, but you have to be careful when you're setting it up. So in the study, we had people perform running for 1 minute, and we didn't have any issues with sensors becoming unplugged. You can also, what I've been doing, because we recently started using this for a study in the wild where we record motion all day, is we can hot glue the sensors into the connectors, and that's been really robust. So they sell different lengths off the shelf, and you just, for the person, pick the correct lengths that works well for them. And then we've had no disconnects over something like 40 hours of recording for people, but it does take a little more upfront work to make sure you're routing it carefully.
Great. Okay, Samantha, next question for you from Ajit. Nice job. Maybe I missed it, but how much range was there in the population in age or knee health?
Yeah, so there was not a large range of population or knee health. It was all young females who were healthy. So in the future, we would like to have a more diverse population. So the model will be more generalizable in the real world.
Okay, I think we're good on questions. I'll send the rest of these questions out to the presenters so you can follow up with a person asking outside of this conference.
Okay. Cool. So our next kind of grouping that we have here is going to be kicked off with Sara Harper. Sara Harper's presentation.
Yep.
All loaded up. Looks good.
Working on it. All right. Hi, thank you. Yeah, I'm Sara Harper. I'm from the University of Wisconsin. I'd, of course, like to thank my collaborators, and I'm here today to talk to you about our foray into the fusion of wearable metrics in order to estimate work output during outdoor locomotion. So it's been studied in the lab before that work demands are different between differing tasks, such as uphill versus downhill walking. But the question becomes, how do we quantify this when we go outside the lab? So to get measures of work, we need to combine measures of kinetics and measures of kinematics. And separately, these have each previously been explored using shear wave tensiometry, which provides a measure of tendon force assumed from the propagation speed of a wave induced in the tendon, and inertial measurement units, which, as others have mentioned, can be used to ascertain things like joint angles. And plotting these against each other after doing some calculations to estimate force and excursion, we can obtain a work loop, which from the directionality and the size of the loop, we can have a more comprehensive view of the overall muscle performance during a cyclic task such as walking. So with the goal to combine these and get those work loops, we implemented a new custom data logger built off of a Raspberry Pi to synchronously record our accelerometry data from our tensiometer alongside a lower body set of IMUs. And we sent 11 healthy young participants out along an 800-meter sloped course that was up a steep hill that involved slopes from negative to positive 10 degrees. So after all of this, we amassed nearly 5,000 strides. And for each stride, we binned them into what you can see on the right there are our raw measures of wave speed, ankle angle, and knee angle. And I'm going to briefly gloss over some details of our processing pipeline to get our estimates of work. So using some generic joint angle to moment arm relationships and a calibration procedure, we can obtain measures of Achilles tendon force and estimates of muscle tendon lengthening due to rotation about the knee and the ankle. And we can split the analysis up between the gastrocnemius and the soleus muscle And finally, for each of these muscles, we can combine our measures of force and excursion to integrate network. All right, so plotting some of those metrics against each other, we've got force versus excursion, and we can see we've got two duplicates of gastrocnemius and soleus at the level walking condition. These are all counterclockwise loops indicating positive network. And as we step through each bend incline scenario, as we increase the incline, you can see the gastroc work loops are shifting, whereas the soleus and expanding. And similarly, on the declines, the gastroc is still shifting and retracting, whereas the soleus is collapsing towards more zero network. So for every single stride, we can plot the network estimated as the area within those loops. And we can see that on average, our network was positive for both muscles across all slopes. And while work scaled with slope, this was certainly more apparent in the uniarticular soleus muscle, where at the steepest slopes, the work performed by the soleus was equal to that of approximately 1/3 of the work done by gravity. And conversely, you can see that the biarticular gastroc muscle is less sensitive, and this kind of reflects that shifting work loop seen previously, which is kind of marked by differing phases of increased knee flexion. So all of these findings really agree with some previous laboratory studies that show that ankle work scales with speed and slope. But with this methodology, we can really take this outside and utilize this in a variety of other activities. Currently, it's based on several assumptions, including physiological cross-sectional area of the muscles and assuming muscle tendon length scale as opposed to fascicle scale. But going forward, we're confident that the establishment of this system will enable us to estimate these metrics in a variety of exciting new applications. And with that, I will thank our funding sources and invite you to follow up with me however you can find me. Thank you.
Okay, thank you very much. For our next presentation, we have Reed Gerchick.
You see my screen okay?
All clear.
My name is Reed Gurchiek. I'm a postdoc at Stanford. This work was done at the University of Vermont. I'd like to recognize my co-authors, Nicole Donahue, Nicola Fiorentino, and Ryan McGinnis. And today I'll be presenting to you a method that we developed to simulate muscle contraction during walking gait using a minimal set of wearable sensors. So more and more researchers are using wearables to monitor patients with musculoskeletal conditions in remote environments. And this makes sense. After all, it's mechanical stimuli that drive tissue adaptation. And there's many wearables-based methods that have been developed that can characterize those important mechanics. However, in this literature review, we found that these methods are not the ones that are being deployed for remote monitoring. By far, the most common outcome variable in these studies is some index of physical activity, compared to very few that have characterized gait on a stride-by-stride level. Several barriers to translation have been identified, and probably the largest culprit is that the sensor arrays are too complex. It requires too many sensors to be deployed feasibly. So machine learning algorithms are being proposed as a solution where you take inputs from a reduced sensor array and map them to biomechanical outputs of interest. However, this approach doesn't generalize as well, and it's less interpretable when compared to physics-based simulation. In reality, there are physical relationships between sensor signal inputs and biomechanical output variables, and the machine learning models have to learn these physics. So in this work, we developed a hybrid approach where we try to decouple the two. Basically, we use physics wherever we can and machine learning everywhere else. So implementing this idea in this work to characterize muscle and joint mechanics during gait looks something like this. So at a high level, this depicts an IMU and EMG-driven simulation of muscle contraction. This here is the physics piece, and we use machine learning only here to map a subset of muscle excitations to a full set. Since this is a new method, I'll briefly describe each of these blocks. So inertial sensor data from only 2 IMUs, one on the shank and one on the thigh, are used to simulate the system kinematics. I'll refer to this as inertial motion capture. This animation compares our IMU-driven solution to optical motion capture. The kinematics of the thigh and the shank were determined just from data from the 2 IMUs, and then the foot kinematics were solved for given the shank kinematics and a simple model for the foot-ground interaction. And that was done to avoid having to place a sensor on the foot. So given this solution for the system kinematics, along with a calibrated musculoskeletal model, we compute the length of each MTU and the moment arm about various joint degrees of freedom. MTU length then is an input to the contraction dynamics along with an activation signal. Muscle force is an output here, and it interacts with the moment arm from which we can compute joint moment. This activation signal also has dynamics driven by an excitation signal, and that's one for each muscle. And this full set of excitations here is required for the simulation. We inform it using a subset of measured excitations, and this drastically reduces the number of required sensors. We call this mapping from a subset of excitations to the excitation of a synergistic muscle, a muscle synergy function. And in this work, we approximated these functions using Gaussian process regression. More details about that process can be shown in this paper here. So we use this approach to characterize the mechanics of the knee joint and the associated muscles for walking gait for 9 subjects, 3 trials each, and they walked at a self-selected speed. EMG data from 3 muscles were used in this wearables-only method. That was the vastus medialis, and then both the lateral and medial heads of the gastrocnemius. These validation results were recently published, so for a more detailed description of the analysis, please see the manuscript. Also, all code used for the research, along with an example data set and scripts for processing those data, can be found at this repo. So shown here are scatter plots of cumulative muscle work done by each muscle during the stance phase for the type of contraction in which each muscle did the most work. So that's either concentric, which are the triangles, and eccentric, which are the circles. Each data point is for a different subject. Estimates from the proposed technique are on the x-axis in each figure, and those were strongly correlated with reference measures, which are shown on the y-axis. And the reference measures was based off of an optical motion capture and a full set of electrodes. So the ability to characterize muscle work in this way provides an avenue for monitoring cumulative muscle load continuously, and it could help us better understand how muscle recovers following disuse and injury, and importantly, for subject-specific dose-response relationships. Net knee flexion moment from our wearables-only method, which is shown in red here, compared well to both the reference EMG-driven technique, shown in blue, and inverse dynamics in black. Compared to the ground truth inverse dynamics analysis, we observed strong correlations and relatively low errors. That's the statistics shown in green there. And those compare well to state-of-the-art methods and wearables-only physics-based techniques. However, here we use a significant reduction in sensor array complexity. And we purposely chose the sensor locations that we did such that they were close to the knee joint, so it would facilitate instrumentation of a knee brace that includes all of the required sensors in order to deploy this technique in practice. A prototype is shown here, and further development is underway. Thank you for listening. I'd like to recognize our funding source, NASA, through the Vermont Space Grant Consortium. Thanks.
Okay, thank you very much, Reed. Our next presentation is going to be by Jack Martin. All clear.
Sorry about that. Forgot to unmute. So today I'm going to talk about some development work we've been doing, trying to incorporate machine learning methods into shear wave tensiometry. And as Sarah talked about earlier, shear wave tensiometry involves inducing and tracking shear waves in a tendon. And if we can measure how fast those waves are traveling, we can get an estimate of tendon stress, because theoretically stress is related to wave speed squared. So we've done this in all kinds of experiments now, measuring Achilles tendon wave speeds, as well as kinematics and ground reaction forces. And if you look at the Achilles tendon wave speeds during walking and running, you can tell pretty quickly that they do a good job of matching what you'd expect for Achilles tendon loading patterns. You compare those to what you can get via ankle torques from inverse kinematics and dynamics, you see this really nice linear relationship between the two across various walking and running speeds. But the issue is that when you look at this across multiple subjects in different colors here, that linear relationship often differs between those subjects. Regardless of exactly why that's happening, that does mean that we've needed to do some sort of calibration if we're going to go from wave speeds to stresses. And so what we started wondering is whether there's more information available in the data that we're collecting than what we're actually using. So this is what we get after each tap. We get these waveforms recorded by our accelerometers, and we take those and we calculate one wave speed point that we relate to tendon stress. But this accelerometer data is actually pretty rich. You've got big variations in acceleration magnitudes, frequency content, damping, all kinds of things. And what we'd like to do is see if we can extract those things and actually relate them also to tendon stress in a way that eliminates the need for calibration. And so to extract that, what we've tried to do is combine the data from those two accelerometers and collect that data over the 12 subjects and 10 gait speeds I showed. Do then principal component analysis to try and quantify how these waves vary across all of those data points in our data set. And when you do that, you can pretty quickly start to see some interesting patterns emerge. So this is showing the first three principal component scores on the axes, and then stress in color coded from it's blue to high is red. And you see that stress seems to increase along this sort of parametric pathway in three-dimensional space. And given that there's this sort of nonlinear relationship between stress and these principal components, it seems that a neural network approach might be a nice way of predicting stress from that data. And so that's what we did. We tried to train artificial neural networks to predict tendon stresses from those principal component scores derived from our acceleration data. I don't have time to get into details, but we used a bootstrap aggregation approach with 10 subjects as training and validation data, and 2 subjects held out to the end for model testing. So jumping straight to the results of that, this is showing how our model performed on the training and validation data, predicted stress from the neural network models on the y-axis, and inverse dynamics estimates of stress on the x-axis. So we've got this nice clustering of our data around the 1-to-1 line here, meaning that our predictions are doing pretty well. And that's particularly nice in contrast to what I showed you with the spread in wave speed versus stress earlier. But more importantly, this is performing well on our test data, which wasn't included in model training at all. And that just means that we're getting good predictions without overfitting the data. Looking at this a different way, that corresponds with really nice estimates of Achilles tendon stress during both walking and running at a variety of speeds. And just to reiterate, that means that we're taking these raw waveform data that we get by tapping on the tendon, and we're using those to predict a tendon stress without any calibration happening here. And that really is a pretty cool result for us moving forward. So the big takeaway from what I've shown here is that this type of machine learning approach could reduce or eliminate the need for calibration when going from shear wave propagation now to tendon stress estimates. And that could be particularly useful for the wearable implementation that Sara showed a couple presentations ago, where you don't necessarily always have a nice opportunity for calibration. It reduces time demands on users at the time of testing. And really that workload then gets moved to sort of the development side, where it means collection of training data to address different applications. With that, thanks for your attention, and thanks to Emily, Isaac, and Sara who collected the data that I tried this on. Thanks to our funding sources as well.
Okay, thank you very much, Jack Martin. As a reminder, everyone, please place your questions that you have for each one of the presenters using their name, first or number, and place those in the chat, and we'll be happy to convey those questions as we move forward. Our last presenter for this section is Lauren Grohowski.
Can you see my screen?
Yep, all good.
Awesome. Well, thank you all for attending this session. Now imagine training day after day for a big marathon or race, feet hitting the pavement over and over, feeling yourself getting stronger, when all of a sudden your shins start to hurt. Maybe you keep running and training, but eventually you have to stop and that dream of the race disappears as the stress fractures form. Stress fractures affect as many as 15% of runners. So what if we could find a way to save that dream and prevent these stress fractures? Well, that's where wearable sensors come into play. My project looks to address this problem of stress fractures with as few wearable sensors as possible by using a pressure insole segmented into 3 regions and a single inertial measurement unit. By finding accurate estimations of tibia force, we would be able to alert athletes to pause or reduce training before these injuries occur. We've seen before that using an inertial measurement unit and an insole should theoretically be sufficient to accurately estimate tibia force, but in practice, it's much more difficult than that. An entire insole as a feature doesn't get the job done, so we have to look to a new way of processing the data. But let's first talk about why an entire insole doesn't produce accurate results. We're looking to achieve tibia estimations similar to the lab-based sensor set as seen on the graph on the screen. We're comparing tibia force estimations from the lab-based values on the y-axis to our simulated sensor set on the x-axis. The simulated sensor set represents what ideal wearable sensors would be without any noise or excess forces between the insole in the shoe and the shoe in the foot. Now, if we use the entire insole as a feature, we have an error value of 11%, which is very poor. An insole by itself is an extremely variable sensor due to differences in running patterns during an individual's run and also between different runners. So in order to increase the accuracy of tibia force estimations without adding more sensors, we're looking to change the way we process the data. In my study, we're segmenting the insole into 3 regions. To create this segmented sensor set, we took the raw data from the insole and split the force values into 3 regions, fore, mid, and heel by equal thirds. All of the sensors in each regions were then composed into one equivalent sensor value. Then each step from different running trials was parsed to create the features of peak force, impulse, and time at which force is exported in that region. These 3 features were applied to the fore, mid, and heel sections, totaling to 9 different features. Finally, we developed a machine learning algorithm enlisting a linear lasso regression to estimate peak tibial force. Now, we're looking to compare our simulated wearable estimations to the new segmented insole sensor set. As a reminder, with the entire insole, there was an error of 11%, which is too high to be usable. But by segmenting the insole, we see an incredible reduction of error of 8%, where the simulated and segmented sets have very similar estimations of tibial force, showing that processing the insole data into segmented regions immensely increases accuracy and helps maximize the potential of the insole. So why do these segmented features produce such accurate estimations? Well, first of all, we can look at the feature importance from the machine learning program. In the top 3 features that contribute most significantly, 2 of them are segmented insole features, specifically peak fore force and fore impulse. The reason for this may be because of natural human gait. Typically, a stride consists of a heel strike to a toe off. Even if the stride changes from heel strike to perhaps running on their toes, there's still force exported in that fore region of the foot. So it's possible that because force is always exported in the fore section of the foot, the feature is less variable and more consistent, therefore more easily connected to estimate peak tibial force. As we've said before, an IMU and pressure insole should theoretically be able to estimate tibia force, but it's difficult in practice due to the variabilities and inconsistencies found in the entire insole. But we found a solution to this problem by segmenting the insole into regions and allowing each of those regions to be features rather than just using the entire insole. As a result, we've seen an 8% increase in accuracy. Therefore, processing the insole using this segmentation technique maximizes the potential of the insole and allows us to achieve accurate estimations without increasing the number of sensors. If you're a runner, you should be excited. Soon, you can run and train without having to worry about stress fractures slowing you down. Thank you, and feel free to reach out to me with any other questions.
All right, thank you all. So I'm going to start with a couple questions. So going back to Sara, do you think the same wearable system could be used to measure gastroc and soleus work during running? Or are there any other activities that you think could affect the accuracy of your system?
That's a great question. So kind of on my last slide, I hinted at, we have a couple different projects that are gearing up to start collecting data. And personally, I'm looking to use it in athletic settings where people definitely will be running and jumping. We collect everything at least 100 Hertz. And we're confident that that'll be fast enough. It's been fast enough in laboratory studies with running before to maintain that accuracy. So we're excited. We should be good to go.
Great, thanks. And then a question for Reed. Is there a particular type of population that you're targeting, or do you have ideas for how the system might be used clinically? Like my mind immediately goes to something like biofeedback, like participants can actively see their results as they're doing a particular activity. So what are your next steps with that?
Yeah, great question. Thank you, Heather. Biofeedback is certainly a potential application. It was motivated by wanting to monitor ACL patients who are recovering from a reconstructive surgery of the ACL. Are probably going to be wearing a brace in the first 6 weeks, and recovery of quadriceps function is really important there, and it's really vulnerable. So some people respond better than others, and to understand why some people respond might have something to do with how they load their quadriceps. And so that's the intended use of this system. That's where we're trying to get the brace instrumented and probably put it on a patient sometime within the next year.
So I'm going to take over for our next two presenters. So first, Jack Martin. I had a question. First, can you talk us a little bit through what patient or clinical populations you might target?
Yeah, so on the Achilles side, we'd be interested in all kinds of things related to Achilles injuries themselves, but also anything that changes the way people load their tendons. So typically think of this as a way to measure how people are coordinating their gait rather than thinking of it as a way to measure tendon health. So if you have a calf injury, for instance, we might be able to see how different from normal are you during running or compared to your other leg. And we could use that to track recovery as you sort of approach a normative population or approach symmetry across your legs. So typically we think of any injuries that would reduce symmetry and Achilles tendon loading, or also patellar tendon loading, as we do collections on the knee as well.
Cool. Also, could you talk us a little bit about your selection for the neural network? So I saw that it looked like you were using the feed forward. It's kind of something that's been brought up before. What was your thinking as you kind of work through the possibilities, or are you trying to manage for time computation, et cetera?
So I will say I'm a novice at the machine learning techniques, but basically this was just proof of concept. So we're not necessarily trying to optimize things yet. This was just to see, can that additional information help us get predictions without calibration? And given that the answer seems to be yes here, now we can start to figure out what the best way to do that is going to be.
Sure. Cool. Thank you very much. And we do have a couple of questions from the audience that I'll check for Lauren. So first, we have a comment that great presentation, love the energy. Second, let's see, question was, were the segments always the same for every subject, or did you look at user-specific data to determine exactly which sensor should be placed in each session?
Yeah, the segments were the same for each subject, and it was just equal thirds of the insole. And the reason that I don't think we need to necessarily look at user-specific data to determine those regions is that already by thirds, it eliminates a lot of the variability that comes from, let's say, runner's arches. That midsection, it creates a lot of variability if you have a flat arch versus a really high arch, because interacts with the insole in different ways. So that variability is already eliminated if it's its own region. And yeah, so I think it would be interesting to look into if changing that section of the 4 would impact accuracy or increase accuracy in any way. But no, for our study, they were all the same.
Next, we have a question kind of pairing together Lauren and Samantha from previously. The question is, do either of you have thoughts on the idea of using regions versus a limited set of sensors in the insole?
Yeah, I'll speak first and then throw it over to Samantha. I definitely think that we could use limited number of sensors. I think that what I found in my study is that if we created an insole that had most of its sensors in the 4 region, rather than an even number of sensors distributed throughout the foot, we could still achieve accurate results and limit the number of sensors there, which maybe would increase battery life because there's less data that has to be collected. But that's my thought.
Yeah, I agree with that as well. I think having more options for sensor location, starting off with a region, could be useful to figure out where to specifically put sensors in the future. But I picture having individual sensors being cheaper in the long run and easier to maintain with battery and in general.
Cool. All right, and we got time for one more. So Lauren, have you compared these results with IMU data alone?
In our larger tibia study, this is kind of a sub-study on it. We do look at that, but in my sub-study, we're not, because in order for us to find the most non-disruptive sensor set as possible, we wanted to use things that could be placed inside the shoe and didn't have to be placed on like a bone or a muscle, because as a consumer, if this were to be a consumed product, that's not something you could get correct every time, and then that would affect your data. So that's why we only look to use the one IMU that's under the tongue of the shoe and the insole.
All right. Well, thank you, everyone. We are going to move forwards with our last section. We'll start off with a presentation by Adam Yoder. As a reminder, again, the presenters will all be available in S4 Muybridge, the spatial chat, if you have any further questions that maybe we didn't get to during this time. All right, take it away, Adam.
All right, can you see and hear me all right?
Yes, we can.
Instrumented sway assessments have proven useful to identify early onset of degraded posture control and fall risk in a number of clinical populations. While persons with lower extremity amputation have similar issues, these assessments are not quite as common in this population. These assessments are usually done by standing on a force plate and extracting temporal spatial features from the center of pressure trajectory, comparing those scores to a reference group or perhaps across time to assess performance. However, there's some pretty clear barriers to widespread clinical use, including the cumbersome equipment required and really the ever-increasing array of sway parameters that has arisen over the years that sort of confounds what we should really be focusing on. So given that, we set our aim to assess postural sway of persons with unilateral lower extremity amputation using a single wearable sensor. And after that, to extract principal features of sway towards recommending a more concise and non-redundant parameter set to facilitate clinical adoption. 49 participants completed this study. They were a mix of transtibial and transfemoral levels of amputation. The protocol is a quick, quiet standing trial of 30 seconds on firm ground with eyes open and then closed. They wore a triaxial accelerometer over their sacrum, approximating center of mass sway, which has prior been validated versus force plate derived measures. From the gravity-corrected planar accelerations, 14 sway parameters were extracted, comprised of the 8 variables in this table. in terms of medial-lateral and anterior posterior components in some of them. Then briefly, we performed a dimensionality reduction and feature selection approach based on some prior similar work that performed a PCA analysis on the eyes open and eyes closed data separately towards describing what underlying features related back to some of the original variables. So jumping right into results, the result of the PCA analysis is initially 14 new variables that are combinations of the original variables. We observed that for both the open and closed conditions, only between 5 and 6 PCs were needed to capture 90% of the cumulative variance. So I'll just be discussing those for the remainder of the talk. So while these reduced 6 PCs are great, they're also pretty abstract and not palatable for clinical applications unless they have some sort of physical meaning. So we can explore that through inspection of what are called loadings that are in effect the correlations back with the original variables. So for example, PC number 1, which captured 40% of the variance, appeared to describe and be measuring the overall planar size of the trajectory, along with some underlying postural corrections based on the most strongly loaded variables shown at right or at left, which range -1 to 1. PC number 2, in contrast, around 20% of the variance, looked to be capturing an increased visual dependency for sagittal balance that has been already reported in this patient population with limb loss due to loss of that somatization in the foot. PC number 3 appeared to be detecting lateral asymmetries that could arise from the unilateral amputation, in that it was most loaded by the ellipse rotation and 2 spectral features in the medial lateral direction only. PCs 4 to 6 weren't loaded by any single primary variable, or a combination of spectral features and this parameter called jerk. But back to our original aim, we also hope to, in addition to developing these PCs, recommend a concise variable set of the original variables that might be used for clinical applications, and I've highlighted 5 of those that we'd recommend for that purpose from each independent PC. So to conclude, we saw that efficient sway assessment was feasible on persons with amputation, and also produced ranges comparable with prior work on uninjured persons and those with Parkinson's disease. The concise and independent set that we recommend here of the original variables also compares well with a similar study using PCA analysis on persons without amputation, with the addition of jerk that we recommend. For next steps, since this is still at the feature engineering stage, we of course hope to use these data to explore machine learning applications, which would classify self-reported pain, mobility, and prosthetic satisfaction in this population that we're also recording in the protocol. And that would be towards informing more efficient and earlier interventions for balance, fall risk, and low back pain across this population. Thank you.
All right, thank you very much, Adam. Our next presenter is Ava Segal.
One second here.
Sure.
Let me get to my, okay. Yes, can you see me and hear the slides? Okay.
Yep, it's all running.
Okay, great. My name is Ava Segal, and I'd like to acknowledge my co-authors and talk about, after more than a year of virtual meetings, I think we've all experienced fatigue from way too much screen time. So today, I'm going to be presenting an alternative to gamifying rehabilitation that pulls us out from behind our screens using robotic feedback and balance training, with the potential to provide assessments of balance performance in a home environment. So falling is a common problem in aging adults, where about 1/3 of the population falls each year. These falls have serious consequences. You're about 2 times as likely to have a serious injury if you fall when you're older, and you have a 7-fold increased mortality rate. This increased fall risk is linked to a steady decline in balance that's associated with aging. And this has been measured by an increasing center of pressure sway velocity. But don't worry, you're not doomed. Balance control is a learned and adaptive skill that can be retrained even later in life. In fact, a targeted and demanding training approach has been shown to be effective at reducing falls. So one standard approach to training balance deficiencies involves a series of double limb static and dynamic movements while standing on a board with multi-axial rotation, as you see here. This approach has been shown to improve functional balance in a variety of populations. However, to be effective, it requires a high number of repetitions, which can be boring and lack engagement. This results in reduced compliance and lower doses, which can hinder long-term recovery. So to improve engagement, a goal-directed training approach, or exergames, has been developed, which provides user feedback typically presented on a computer screen to promote motor learning and shift attention away from the movement outcome. And while this approach has been shown to improve adherence to therapy programs, there are several barriers to use that exist, including high complexity and cost, as well as a lack of portability. Also, excessive screen time can be detrimental to your health, including physical, psychological, and neurological effects. So one non-screen feedback approach uses wearable sensors to control a physical robot in a real-world environment. In a study of older adults performing an upper extremity task, the elderly subjects reported that they enjoyed the robotic feedback more than feedback coming from a screen. So we asked the question, can balance performance be assessed at home with lab-level accuracy? And to answer this question, we designed a gesture-controlled robotic balance training system that uses an IMU-based gesture controller to send wobble board pitch and roll angles wirelessly to a robotic car platform. Then the human must perceive, plan, coordinate, and execute movements to achieve the desired trajectory through musculoskeletal and sensory motor control. This low-cost system is small and can be easily attached to different body segments or training modalities, and uses a microcomputer for high-level processing and onboard data acquisition. Through this testing paradigm, our vision is to achieve personalized balance training that quantifies recovery progress in a home environment. So our first step to achieve this goal is to validate the onboard IMU signals with established laboratory measurements. Therefore, we conducted a pilot biomechanics experiment to assess the potential of the system. Sway was defined as the IMU pitch and roll angles, and this was compared to two gold standard motion capture measurements, the wobble board angle and the center of pressure position. Sway velocity was the first order finite difference of sway, and then we calculated the Pearson correlation coefficients for each signal pair across conditions. So here I have representative plots of pitch and roll sway trajectories that have been normalized to the peak rectified signals along the y-axis, and this is across a 10-second time frame along the x-axis. Our overall results demonstrated a strong correlation between signal pairs for all conditions. Similar plots for sway velocity showed a strong correlation, but slightly less strong than sway, and about twice as variable. This is likely due to noise with signal differentiation. So these results demonstrate the potential for tracking training progress using a low-cost gesture controller sensor. And this could reduce therapy time and cost, as well as promote long-term adherence and the efficacy of at-home training programs. Our next step is to conduct a full validation study across age groups. And then we also plan to compare robotic and screen-based feedback by studying the biomechanical strategies, motor learning, and engagement of both younger and older adults. So at this time, I'd like to acknowledge my funding source and once again, thank my co-authors. And I'd be happy to take any questions. Thank you so much for listening.
Thank you so much, Eva. All right. Our next presentation or presenter is going to be Anita Basaveda. There it goes. I see your screen. You're still muted.
Sorry about that. Thank you. So thanks for having me here. My talk is on the effects of stress and on neck muscle activity and postural sway. And I want to acknowledge first my co-author, Keaton Zimbelman, who did this work as his undergraduate honors thesis in neuroscience at Washington State University. So the motivation for this was really that most of us will experience neck pain sometime in our life. And there are multiple risk factors for neck pain. And two that I'm going to focus on here, or two sets of factors, are the biomechanical risk factors, which we are all pretty familiar with, and also psychosocial risk factors. So things like stress, depression, and the satisfaction and maybe reasonable or unreasonable demands on the job that can also lead to pain. And of course, these kinds of factors can also interact and influence each other. So the aim of our work was to examine the effect of social evaluative stress on neck muscle activity and postural sway during computer task. And social evaluative stress, which we'll call SES during this talk, is the stress response that occurs when someone is evaluated in a negative or threatening manner. It's sometimes referred to as social evaluative stress. And so we hypothesized that during a computer task that involves social evaluative stress, we would see a decrease in postural sway and an increase in neck muscle activity. So this implies some kind of stiffening strategy that could lead to increased mechanical loads that are implicated in pain. So to apply stress to our subjects, we use the Montreal Imaging Stress Task. This is a computer program that is based on psychological application of social evaluative stress. It's based on something called the Trier social stress test, if you are familiar with that. But this was a way to apply it in a seated computer application. So the MIST task has two different conditions that I'm going to talk about. The first is just a math condition. So subjects were doing challenging mental arithmetic. The problem shown here is somewhat easy, but they get harder and a little more difficult and frustrating as it goes on, even for engineers, I felt. And then the social evaluative stress condition, the SES condition, was the mental arithmetic with the added stressors of time constraint and evaluative feedback. And that evaluative feedback consists of people are told that they have to achieve a certain % correct in their scores. And they're also deceived about how well they're doing. So they're told that they're doing not as doing worse than they actually are. And then the investigator can kind of hover around behind and make the participant a little more nervous, in fact. So while subjects were doing this task, we had IMUs on the head and the trunk. And we had EMGs on 3 neck muscles bilaterally, the sternocleidomastoid, right here, the trapezius, and the semispinalis. So what we found, first of all, we just confirmed that we were able in our lab to induce social evaluative stress. We found, first of all, when we measured stress and neck discomfort on a 0 to 10 visual analog scale, that both stress and neck discomfort increased in the SES condition. And neck discomfort in particular is important because it's a predictor of future pain. So we also found when we measured head median acceleration that the acceleration of the head was greatest in this SES or social evaluative stress condition and less in the math condition. And those were both greater than the the acceleration during a resting condition with eyes closed. So this was actually opposite to our hypothesis. And in watching the subjects, we feel that some of this acceleration may have been occurring due to a frustration with the task as they're getting wrong answers on the math questions. And then finally, when looking at the muscle activation, we only found increased muscle activity in the posterior muscles, that's the trapezius and the semispinalis, and no change in the sternocleidomastoid. And specifically, we found that the muscle activity was slightly greater during both the social evaluative stress and the math condition compared to the resting condition. And it was only statistically significant for the right trapezius and the left semispinalis, although all of 4 of these muscles kind of trended towards significance. So that implies that the math task alone might be sufficient to increase neck muscle activity. So kind of in conclusion, we found that the MIST program is an effective protocol to assess the effects of stressful computer work on certain parameters that are determinants of neck pain. In the future, we'd like to know if we can use these IMU measurements of muscle activation and sway to infer actual stress and mechanical loads in the spine. And eventually, we would like to look at interventions, stress-reducing interventions, things like mindfulness meditation or other forms of relaxation and look at how those might affect the biomechanical and psychological determinants of neck pain. So I'd just like to acknowledge a couple of other students who helped with this project at the WSU Honors College. Thank you.
All right, thank you very much, Anita. Our last presenter for this section is Mohazal.
Can you see my screen?
Yes, we can, and we hear you fine.
All right. Thank you for the introduction. Before I start, I would like to thank my advisor, Dr. Corey Pugh, for the assistance with this project. Classification and prediction of human movement has become an important research topic in the field of biomechanics and health. Researchers use body-worn sensors such as IMU, EMG, goniometers, and force sensors to measure human movement in real time. They also use machine learning algorithms to classify and predict the intended outcomes for the devices. In a typical machine learning application, we have a set of data points for training a model. The raw data may not be in the form that is applicable to all algorithms. Therefore, practitioners may have to apply appropriate data pre-processing and feature engineering to make this data amenable for all algorithms. After taking these steps, they must perform algorithm selection and hyperparameter optimization to maximize the predictive performance of their models. Each of these steps may be challenging, resulting in significant hurdles for the use of machine learning. If we were able to automatize this process, we could dramatically simplify these steps for non-experts. As a result, the objective of this project is to make an application which guides the user for best practice when implementing machine learning with human movement data. In this slide, I'm going to explain how our model works. After importing the data, the software starts processing by constructing some features out of these data. Here you can see the list of these features. Then these features are analyzed over time using a sliding window where the size and overlap of the window can affect the feature usefulness. Use the chi-square test for feature selection. Use genetic algorithms to optimize the window length, overlap, and finding the best number for features. Finally, we use 5-fold cross-validation to generate stable models, and accuracy was the metric which we used to compare the predictive performance of different models. To validate the method I just described to you, we used a dataset from a previous study which looked at 3 machine learning algorithms, including support vector machine, k-nearest neighbor, and ensemble trees for finding the best algorithm for turn predictions. The raw data was collected from 5 amputee subjects. In this study, we are going to use our new technique, and we want to compare the older manual and our new AutoML version. Results show that windowing and optimization led to considerable improvement in the accuracy for each algorithm. As you can see, the accuracy for support vector machine was increased by 4% on average. We saw 5% improvement in the accuracy for k-nearest neighbor and 6% improvement in accuracy for ensemble trees on average. In this table, we can see that each user has a specific window size, which is different from pooled data. This means that personalization will benefit the user with higher accuracy. Furthermore, the optimal value for window size is different from one algorithm to another for a specific subject. The key takeaway from this presentation is that the manual methods are inefficient and automating the process can give us higher accuracy, and higher accuracy could lead to better outcomes for patients. Secondly, these algorithms really need personalization. Currently, these algorithms are trained by pooled data which belong to a large number of different individuals, and then they're used by a patient who has their own specific stride. Since the algorithm is trained by different data, the amputee might not feel as comfortable when using the device. Therefore, creating a customized algorithm which is only trained by the data of the patient could lead to better mobility and higher satisfaction. Finally, the clinical takeaway is that a tool like this can be used by clinicians for creating personalized algorithms in a clinical setting. Here you can see the list of my references. Thank you very much for listening. I'm open to questions, and I would be happy to answer more questions on the spatial chat.
Okay, thank you so much.
Okay, thank you so much.
You'll turn off the screen share, or I can take it. Cool, thank you. All right, so we're going to open up the floor again to questions. So Heather, I believe you're going to get us started, or no?
Sure, I can do that. So one question for Adam. Do you think the selection of variables would change depending on exactly the specific balance task, like if it were single leg stands, or if it was slightly different? Do you think that would change the reduction of those variables at all?
Yeah, my initial inclination would be it probably would, and that we did collect data for the full clinical sensory interaction test, so they stand on foam, in addition to the vision perturbation. So we'll be able to learn a little bit about that. Also, we have some other functional tests like the sit to stand motion that we hope to sort of perform these same feature reduction methods on. So looking forward to exploring that.
As a follow-up, did your participants all kind of have the same level of balance, or do you think that some of them had more poor balance? And how might that have maybe influenced some of your feature reductions?
Yeah, they definitely did. I mean, to the point where some we had to exclude data because they fell during the closed eyes task on a foam surface. Data was not included in this presentation, but it would be of interest to try and predict why those outliers, those fallers fell. And at this point, I think our sample size is about doubled from what was in this presentation. So hopefully we'll have the power to explore those kind of prediction tasks.
Great, thank you very much.
All right, I have a question in the chat for Ava from Ajit. Any thoughts on whether the placement of the robot matters?
Yes, so that's a great question. Thank you so much. So gaze definitely matters. And we thought through this quite a bit and looked into the literature. One aspect is that one of the common strategies for navigating uncertain terrain or people with lower balance abilities is to actually look down in front of them. So that in itself is relevant, I think, to be able to train your balance while focusing on the ground. And then when we do our comparisons to the 2D screen, we're going to place the screen in a similar distance so that that is in fact comparable. And it's just about a meter from the person, which is consistent with other studies in the literature.
I also noticed that your participant did a pretty good job considering she was wearing a mask and the shield. So props to the participant there. Did that present additional difficulties?
So thankfully, this was during full lockdown, and we had, extra protection in place to get a little bit of pilot data. It was one of, but then now we are unmasked with the as long as everyone's vaccinated. So that helps. We quickly took away the shield because that was kind of getting in the way, and I think so for future subjects, we shouldn't have to do any of that.
All right, I have the next question for Anita from Michael. How long was each participant performing the tasks in your study, and what was the gender participant breakdown?
Yes, thanks. Sorry, I think I might have accidentally removed that the information about the number of subjects when I was trying to streamline my talk, but we had 10 subjects and it was 6 males and 4 females, all college age students. So that may make a difference. And the tasks were about 5 minutes long each.
Okay, and we have time for one last question for Mojtaba from Peter. Have you already, or do you plan to in the future, compare your genetic algorithm to various deep learning approaches?
Thank you, Peter, for your question. That's a great question. We definitely plan to include more complex models such as line short-term memory and convolutional neural networks. And in this study, we only considered simple algorithms like KNN, SVM, and ensemble trees. Since these algorithms cannot work with raw data, we had to extract some features and have an optimization algorithm for finding the best number of features for these algorithms. But since the ultimate goal is attaining the best accuracy, we definitely plan to include more complex models in the future.
All right, well, I'd like to thank all of our presenters. All did a wonderful job. And a reminder for everyone, the presenters will be available for further questions in S4 Muybridge, the spatial chat. So look forward to receiving more questions from you all. And again, thank you very much for attending the wearable session.
Thank you, everyone. Thanks, moderators and Sam.
Thanks to the moderators too. Appreciate it.
Hey, thank you.
All right, well, thanks everyone. That was awesome.
It helps when they have excellent work. Yeah.
No kidding. Oh my gosh, that was by far one of the most interesting sessions that I've seen in the conference. That was incredible.
Yeah.
Man, oh man.
And I've never felt so bad about being indoors in a lab. So,
I know.
so much of this being out and about and doing things.
I
I'm like,
know,
"God, here I
right?
am sitting here. I should be on my cell phone doing this and going around. So
Oh gosh. This is so cool. Awesome.
cool. Thanks a lot, Sam. And you put this on YouTube, is that right?